Hello, my name is Sherman Ikimoto. I'm a director at Future Facilities. Welcome to Predictive DCIM. It's all about capacity utilization efficiency. This presentation is about the biggest problem facing data center operators today, efficient capacity utilization. We will discuss at a high level the challenge of efficient capacity utilization, why current best practices, which are short-term focused, reduce capacity utilization efficiency, and the financial impact of this loss. A good way to start the presentation is with this quote from Dr. John Koomey, a research fellow at the Steyer-Taylor Center for Energy Policy and Finance at Stanford University. He says data center capacity is an aspirational goal of the design. Achieving this goal falls on the shoulders of operations. Lack of awareness for this fact about the data center is one of the main reasons for the data center capacity performance problems we see today. To start, we must define data center capacity. Data center capacity is the total amount of IT load in kilowatts that the data center can support at the desired levels of redundancy. To support IT equipment, the distributions of space, power, and cooling must be coincident to each other and to the IT configuration. Data center capacity is lost when one or more IT resource becomes unavailable to the units of IT equipment for whatever reason. Capacity utilization efficiency, or CUE, is a measure of how effectively operations is able to hold alignment between the IT and resource distributions. So again, data center capacity is the total amount of IT load in kilowatts that the data center can support at desired levels of redundancy. A time-lapse animation of a data center build-out is helpful for visualizing the capacity utilization efficiency challenge. The first animation shows the original build-out plan that was used to design this data center. In design, the facility is designed around an IT configuration plan that is really just a guess at what will actually be built out by operations. But when operation starts, without fail, the IT build-out plan changes from the design. These changes range from seemingly small physical differences like IT unit size or airflow utilization to large ones such as a new floor layout or IT technology. Any change from the original IT plan that isn't properly integrated to the facility by operations will reduce capacity utilization efficiency. To understand exactly how capacity is lost, data center operations can be equated to the computer game Tetris. Like in the data center animation we just saw, first we will design the Tetris board that we will use later to play the game. Conceptually, data center design is similar to this because we start with a guess at the characteristics of the blocks and how they will be arranged. This is our IT loading assumption. Then we lay out the Tetris board around this arrangement of blocks. This is our data center infrastructure design. And now we are ready to play the game. The data center is ready for operations. In the real game, a different sequence of blocks drops into the fixed space of the Tetris board with little warning. Under time pressure, the blocks must be placed so that they fit together tightly and use the space efficiently. A lack of foresight and time pressure are what fragment the space or capacity of the Tetris board. These are the conditions in the data center that fragment space, power, cooling, and ultimately data center capacity. One difference between Tetris and data center operations is that in the data center you can't stop at a partial load. The load must continue growing. When capacity utilization efficiency is low, the only way to maintain growth is to renovate, relocate, or expand the infrastructure. One additional important difference is that you can't see capacity fragmenting in the data center like you can on the Tetris board. This challenge leads to millions in lost data center capacity, and we will discuss this challenge in more detail. The capacity utilization challenge is recognized by the industry, but not many understand this problem fundamentally, and it gets very little attention relative to other topics, such as energy efficiency. There is good reason for this that we will also cover in this presentation. As Future Facilities, our main business is helping data center operators improve CUE. After looking back at the long list of clients we have helped, we estimate that the typical mixed-use, mission-critical facility will achieve at most 70% capacity utilization rate. At least 30% of these data centers is unusable to support IT equipment. Let's take a look at the impact of CUE on data center total cost of ownership. This graph shows a high-level breakdown of the total spend on a typical Tier 3 data center for a 1 megawatt IT load. The IT hardware capex is left out because it is a fixed value in this comparison. Everything included, for 15 years of operation, 1 megawatt of IT load will cost about $32 million. This covers design, construction, operations, and power over the entire data center lifespan. This calculation, however, assumes that CUE is 100%. This is not the industry norm, as we saw on the previous slide. After factoring in a realistic CUE, we can estimate the true total cost of ownership. When CUE is low, more floor space, infrastructure, operating resources, and energy are needed to support the 1 megawatt of load. This increases the cost of each component, which in turn has a huge impact on total cost. So instead of $32 million per megawatt, the typical operator will end up paying $59 million per megawatt. One final point, a focus on one aspect of data center efficiency, like cooling system efficiency, not only misses the real cost savings opportunity, but can actually increase total cost of ownership if done without understanding the impact to the data center system as a whole. Low CUE is by far the biggest financial challenge for a data center operator. Typically, 30% or more of data center capacity will be lost. With so much at stake, why is low CUE so common? Why do so many focus on components of the total cost, like energy efficiency? Low CUE is common because operators lose sight of the capacity objective. How does this happen? To understand this, we have to go back to when the data center was first being planned. When a business identifies the need for computing resources, the management team will project computing requirements for 10, 20 years due to the costs involved. The computing requirement is then translated into construction, operating, and energy plans for the entire lifespan of the data center. The integration of these plans sets a total cost of ownership budget for the needed capacity that is signed off by the CFO, CEO, and board of directors. But immediately after sign-off, the budget is fragmented and distributed across operational teams in time. For example, IT will own a portion of the total budget, which on average amounts to about $1 million per year per megawatt of capacity. Their portion of the budget is spread out annually over the lifespan. This practice fragments the objectives of the data center operation and changes the focus from the original integrated budget to annualized operational budgets. As a result, the operational teams undermine the capacity objective and each other, which makes it tough to hold the individual budgets in check. As this occurs, the total cost of capacity skyrockets. And making the situation worse, operators do not track capacity utilization or total cost of ownership. So this massive total cost overrun is invisible to the operator. Let's take a look at an example of losing sight of the capacity objective. In this example, the facilities team has hatched a plan to reduce energy consumption of this data center. They want to replace the standard blowers in the crack units with EC plug fans. This is a popular aftermarket best practice today that seems like a no-brainer because the new fans will deliver the same amount of air at 30% less power. What most people don't know is that the new fans, even though they supply the same amount of air, will change the distribution of cooling to the IT configuration. This is the capacity distribution of the original fans. Every U slot is green because space, power, and cooling is available to each unit of this plan. This is the capacity distribution of the new fans. Many of the U slots have turned red because one or more of the IT resources is not available to the entire IT plan. In this case, cooling is the limiting resource. The new fans move some of the cooling from the IT plan to where it is not needed. This cannot be seen or measured. This is a problem because on a later date, operations will install IT equipment where cooling is supposed to be, but they won't know that it isn't there until they install and turn on the equipment. In this case, 75 kilowatts of fan power was saved, but 120 kilowatts of capacity was lost. In terms of total cost of ownership, $50,000 per year in energy costs was saved, but $465,000 worth of computing capacity was lost. So efficiency was gained at the expense of capacity. a classic case of being penny wise and pound foolish. Here is an example of a change to the IT plan that, when done in isolation, turns out to be penny wise and pound foolish also. The IT team has discovered a new pod technology that provides the performance they're looking for. The space and power requirements are about the same, so they assume the change will be fine. Again, here is the capacity distribution of the original plan. Here is the capacity distribution of the new plan. Without this view of capacity, IT doesn't know that the new pod has thrown cooling out of alignment to the IT configuration. Again, the only way to keep going is to renovate, relocate, or expand. CUE problems start with the way operators spend money on the data center. The total spend is fragmented and distributed. This causes operators to lose sight of the capacity objective. Today, tracking of total cost of ownership is not a standard practice. This is a primary reason for losing sight of the objective. In addition to how the money is spent, are there other operational practices that contribute to losing sight of the objective? Actually, there is. Data center capacity monitoring is not a standard practice today. Instead, the industry is fixated on monitoring power utilization and environmental conditions. This is what is being offered by DCIM tools. Let's take a closer look at the data center build-out example we saw earlier. This time we will monitor power utilization as the IT configuration is built out. As the IT equipment is installed, power and space utilization proceeds as planned. And early on, the operator doesn't detect problems and allows the build-out to continue at a pace set by the IT groups. But at mid-life, cooling and power problems appear for the first time. Of course, this shouldn't be happening because only 1/2 of the total power has been used. At this moment, panic sets in because the IT services need to be up and running, and under pressure, the teams are forced to do what it takes to continue the build-out, which is, as Gartner says, renovate, relocate, or expand. But obviously, there's a problem here that we cannot see. What if data center capacity could be monitored in real time alongside power? The data center starts operation at 100% available capacity and 0% power utilization. On day 1 of operation, we can see available capacity drop drastically, even though the IT build-out has just started. This is typical, and this happens because the actual IT configuration differs from the design assumptions. These include things like cabinet geometry, IT unit size, airflow utilization, and placement in the cabinets. Again, this effect is real, but goes unseen today because data center capacity isn't being monitored. Operating blind to capacity utilization lulls the operator into a false sense of security as the IT configuration is built out. Typically, 50% or more of the IT configuration is built out before capacity problems become detectable in the form of IT availability problems, like hotspots or power issues. As you would expect, the capacity objective is lost in the absence of capacity monitoring. DCIM tools alone do not provide a view of data center capacity. So in the typical data center, capacity problems form immediately but are discovered months or years later in the form of IT availability problems. This delay is costly for operators because much of the data center is built out by the time they are alerted to the problems. With a clear understanding of the CUE problem, the need for effective data center operations becomes clear. 3 types of real-time information are needed. The operator needs to know that current conditions in the data center, such as environmental conditions and power thresholds, are safe. This is similar to what is provided by the dashboard of a car. The operator needs to see just up ahead to know that the next set of IT or facility plans will work safely. And this is similar to what is provided by the headlights. Many believe that DCIM tools can predict the impact of future plans on availability or capacity, but as we saw in the example, this is a myth. Finally, the operator needs to continuously reroute the data center's path to its intended destination, which is a full IT load, in the face of continuously changing traffic conditions or IT plans. The operator needs a navigation system. DCIM tools can tell you where you are, but not how to get where you want to go. A combination of real-time information from DCIM tools and predictive modeling provides the three types of information required to safely navigate a data center to its destination. Predictive DCIM is based on a mathematical model of the physical data center. This model is effectively a digital clone of the actual facility at every point in time over its lifespan. The model represents the geometric configuration of the facility infrastructure and IT configuration. It also comes with the ability to model space, power, and cooling distributions and how they relate to each other and to the IT configuration. The cooling distribution is the most complicated IT resource to model. Advanced modeling techniques are required. The predictive model uses computational fluid dynamics to determine the distribution of cooling for a given data center configuration. In this walkthrough, we see the model at a snapshot in time. IT and facility configuration updates are submitted to the model through a software graphical user interface or automatically through integration with DCIM tools. Libraries of IT, cooling, and power equipment from all the major vendors are included, so configuration updates and planning is a straightforward process of dragging and dropping from catalogs. As the model is updated over time, by its nature, it reflects the physical integration of the building infrastructure and the IT assets to form a data center system. The predictive model is an inexpensive, risk-free testing ground to predict the performance impact of data center plans and recalculate the path to full capacity when those plans change. The predictive model changes the data center planning process from plan, implement, and react to plan, predict, adapt, and then implement. Predictive modeling is the only way to visualize the formation of capacity problems and address them before they become problems for real. It is also the only way to ensure the path to full capacity. By monitoring capacity in real time, the operator will know about and be able to fix capacity problems as they form. This enables the operator to hold CUE high at all times. This greatly reduces or prevents availability problems like hotspots and power distribution problems, reduces risk, increases lifespan of the data center and perhaps the people operating the data center, and minimizes total cost of ownership. To summarize, capacity utilization is by far the biggest data center problem. 30% or more of data center capacity will be lost in the absence of capacity monitoring and adapting to changing traffic conditions in the data center, which are the IT plans. Capacity fragmentation is caused by changing IT plans and made worse by a lack of capacity monitoring standards. The only solution to the data center capacity challenge and skyrocketing total cost of ownership is predictive DCIM. As far as next steps, we would be happy to present to your team and discuss in detail the problem of low capacity utilization efficiency. Future Facilities also has a new data center performance assessment service called ACE for availability, capacity, and efficiency. This is a fixed price project that ranks the performance of your data center relative to its peak potential. This ranking is a view of how far your data center has drifted from its intended performance and is the basis for calculating the return on improving performance. Also included in the assessment is a new roadmap of physical changes that will raise the ACE ranking. A third option is a pilot project for implementing predictive DCIM. This is also a fixed price project that starts with an ACE assessment and continues with a full implementation of predictive DCIM for maybe 1 or 2 data centers. This project will deliver value for the data centers that are involved in terms of energy and capacity savings. Also, implementation issues are solved so that a rollout to other data centers is as effective as possible. Future Facilities thanks you for viewing this presentation. We hope you found it interesting and informative. Please email us at info@futurefacilities.com for more information. We look forward to seeing you in the future. Thank you again.